for this course we are going to follow only allowable stress design for the whole of the remainder design activities. We will not discuss any further on LRFD. So, basically looking at the picture, I think we did discuss about this few classes back. When you design a structural element means it is not just one simple calculation, you should look at the whole of a member and divide the member into several subsegments, look at the composition of forces on each section. So, you look at a simple in fact quite a simple diagram of bending moment distribution along the length and the shear forces, and you might also have axial force variation, not considerably, axial force normally uniform in most of the sections, but what you might actually have variation is the section properties. You see this picture, at the center we have a different color, means you have a slightly increased thickness because there may be a member coming and connecting somewhere in that location. So, you may have a variable cross sections, changing moment of inertia, changing cross sectional area and changing bending moment diagram and shear force diagram. So, all your design calculations needs to be verified at every section that has got the critical combination of section property lower, higher moment of moment and the forces. So, that means if there is no change in cross section, for example, bending moment diagram is uniform like this or maybe even better than this, like a simply supported diagram, only maximum bending moment is at the center, we know very well. Then you do not need to check at so many sections, you may check at only one section at the middle and forget about it, because you know very well established that section is not changing, moment is maximum there, there is no axial force, shear force is maximum at the extreme ends. I will check the shear at the extreme end, bending moment at the middle. Whereas, if you are not very sure of the variation of the distribution of the forces and the section property changes from location to location, you might divide the whole member into several subsegments. Normally, in offshore we may divide more than 3, 4, sometimes if you have variable cross sections you can divide it into 10 sections. You have to remember the calculations what we are going to learn from now have to be repeated at every cross section and find out which one is the maximum unity check or maximum stresses, and that will be the governing case. Now, the procedure is very clear. What we are looking at is the divide the member into several sections, establish the member forces, establish the section properties like moment of inertia, sectional area, effective length factors, radius of gyration, everything you calculate for each section. Calculate the applied stresses, axial, bending in x direction, bending in y direction maybe, and then bending associated with the hoop stress due to hydrostatic pressure, and then shear stresses at every section. Establish the KL by R ratio for the whole of the member, because even at each section KL by R ratio will not change, KL by R is for the whole of the member, and then find out what is the allowable axial stress, which is what we learned. The whole of allowable stress design is applied stress, calculate the allowable stress, find out the ratio. Now, when you are calculating the allowable stress for axial direction or axial effect, you need to make sure that the buckling is taken into account. That is what we learned earlier, whether the yielding is governing or buckling is governing. As long as you have the cylinder member, buckling may actually make the structure to fail before the yielding starts. So, basically allowable buckling stress needs to be found out in terms of reduction in the applied allowable stresses for axial direction. So, what we normally do is we calculate the allowable stress using the normal yield stress and then try and evaluate whether yielding is going to happen or buckling is going to happen even before that. That means, limit the yield stress to the buckling stress. So, the limiting yielding stress is nothing but the maximum stress at which buckling. In here we got two types of buckling, one is the local buckling, the other one is the global buckling. Global buckling is taken care in terms of Euler buckling length, which is a K factor, but the local buckling has not been taken into account. So, that is what we are going to look at. We calculate the local buckling in terms of elastic buckling stress and inelastic buckling stress. Basically, instead of going to elastic, we also go slightly higher than elastic. The reason why we go for inelastic, because the local buckling, if you limit to elastic only, it will be very high. So, we try to go for reduced, and basically that formula is empirical, we will try to do that. Then establish the d by t ratio, which already you have. Diameter is known, wall thickness is assumed by you only. So, you know the d by t ratio. Find out the allowable bending stress, basically that is the only governing case for bending stress. And finally, you come to hoop stress due to external pressure, and basically due to external pressure again the local buckling will happen. The first one here, the local buckling is due to axial stress, whereas the fourth one, the buckling stress is due to the hydrostatic pressure applied on the outside of the cylinder. And that is why you see the two symbols, the buckling stress due to axial stress is Fxe, whereas hoop stress is called Fhe. So, you please note down the symbol change. If it is axial stress or axial load, corresponding buckling is Fxe, whereas if it is a hoop or basically due to hydrostatic pressure, then it is Fhe, elastic part. The inelastic part is Fxe, and basically that name is changed to critical, basically it is called Fhe. So, there are 4 sets of buckling stresses, one for axial loading, the other one is for hydrostatic, elastic part and inelastic part, that means elastoplastic. Inelastic is nothing but beyond the yield part that you are looking at. Then what we need to establish is the combined effect of all these axial, bending, shear and hoop. Now, you will see that you will also need to make sure that every single component is also lower than the allowable, and also the combined effect is lower than the allowable. In terms of axial allowable, you just simply compare the axial stress applied with axial stress allowable. Similarly, each component. Then we need to do an interaction, because you may have the axial load at the same time when the bending is applied. So, you need to combine them together and see whether the combined effect is within the acceptable. Similarly, the axial stress with the hoop stress, basically you need to make sure that that is also within the limits. Finally, the shear and bending. If you look at a simply supported beam, shear is 0 where the bending moment is maximum, shear is maximum when the bending moment is 0, but elsewhere somewhere else you may also have a bending moment, you may also have a shear force, which may combined effect could create problem. So, you have to look at the shear and bending. So, all these combinations is to make sure that in no situation the structure is stressed beyond the limits supposed to be allowable stress. So, that is the idea behind. So, if you look at how do we calculate the applied stress, I think most of you must, I just repeated here, because many times in the last semester several of them did not know how to calculate applied stress. So, for that purpose I have just listed down the basic mechanics you might have studied in your bachelor's degree second year, and you must remember this for this full course, because you will be repeatedly using this many times, and do not ask for can you tell me the formula for applied axial stress. So, just make sure you refresh this, just for completeness I have given you, so that you can keep it for your records. So, basically the P is the axial load, mx and my are the bending moments associated with the axis of bending x and y, and shear stress basically your V is the shear force, and in this particular case we have taken the half the area of the circular section. You should ask why, basically the direction of shear is you have to find out the effective area. For example, you take a I section, for vertical shear force you only take the web, I think most of you might have studied in your applied mechanics. For horizontal shear you take the area of the flange. So, when you actually make a circle change into a square section, for example, just take the same circular section, hollow section, change into equivalent square hollow section. So, what will happen? Same 50% area will be on the web side, 50% area will be on the flange side, but that is only the crude way of explanation. You actually need to integrate the circular section like what we did in few slides back. You need to integrate the 1/4 of the circle for shear stress distribution. You will get actually 50% of the area is effective in vertical shear, 50% of the area is effective in horizontal shear. And then you have the hoop stress. I think most of you will know how to calculate the hoop stress. Pressure times the diameter is the projected area, divided by 2 wall thicknesses. If you draw the free body diagram of a pipe cut into 2 pieces, 2 wall thickness is effective at any cross section. So, basically that is why we have a hoop stress is P d by 2 t, and I think the area and moment of inertia is well known to all of you. So, basically we need to make sure that you remember these basic principles of calculations of applied stresses, very easy. As long as if you are given the loads like axial, shear, bending, you should be able to calculate the applied stress. The allowable stress is a matter of looking at the member behavior both in terms of cross section and in terms of the length itself. So, basically 3 things: yielding, local buckling, global buckling. Now, if you look at the axial stress, mostly global buckling is taken into account by means of a so called a parameter slenderness ratio. Where it comes from? It comes from back in Euler buckling. We had a simply supported beam is the reference member, the length is L, Euler buckling is say some amount of load, it starts giving global buckling. Now, when you compare that with other members like fixed condition or a cantilever, the load capacity is different. Compared to a simply supported, fixed will carry more load, cantilever will carry less load. So, we actually prorate the effective length. For fixed it will be half length, for cantilever we have double the length because of lesser load, which to carry the same load. So, that is how the K factor was determined. So, the global buckling is taken into account by means of a multiplication factor indirectly, is called a effective length factor. But the local buckling needs to be taken into account by means of computing a local buckling stress, find out whether local buckling is going to happen, then you substitute the value of f x c instead of f y, because it is not going to yield, it is going to buckle. So, basically the limiting yielding stress, we call it the limit yield, because buckling is governing the design. So, instead of a global buckling, local buckling is going to govern the design. So, that means we will replace the f y with the f x c. So, we need to find out f x c first and check whether buckling is happening. If that, then you replace this f y in the equation to calculate the allowable axial stress. So, there are 3 steps. As long as the member is subjected to axial tension load, there is no question of either local buckling or global buckling. So, very simple, allowable stress is a constant which is taken as 60% of the yield stress, very straightforward. So, tension means no tension, easy, but whereas compression you have got a problem, you have to step by step 3 steps you have to calculate and then find out the allowable axial stress. Bending also similar, only it is governed by the slenderness of the tube, basically the diameter to the wall thickness. The more slender, not in terms of length, in terms of its local effect, the cross section is too slender, then it might actually bend easier than the other. So, the maximum is limited to 75% of the yield, but we will prorate according to the d by t ratio. The larger the d by t ratio, lesser the allowable stress, smaller the d by t ratio, higher the allowable stress. So, very simple idea, there is no complication there. Shear stress very straightforward, irrespective of whatever the d by t ratio or KL by R ratio is taken as 40%, also very easy. The last one is the hoop stress, is going to be governed by local buckling, basically the buckling due to slender d by t ratio. So, that is going to be calculated and we will use the FHC as the representative allowable stress, basically the inelastic allowable stress. Now, among these, I think if you look at it, the first one seems to be a little bit complicated, the second, third, fourth also a little bit. So, we will just quickly go through today to try to make understand. We know how to calculate allowable stress, applied stress. If you know allowable stress, then the design can be concluded, because our design equation is applied stress is less than allowable stress, or the allowable stress is greater than applied stress. So, basically if we know these 2 components, the design can be. So, how do we calculate a allowable axial stress? There are 2 components, one is the tension stress or tensile stress, 60%, very straightforward, whereas the compressive stress we got as interaction formula, very simple formula. How it comes is basically based on experiments. As early as 1940s, there is an organization called Column Research Council in UK. They have done a lot of studies, experimental studies, come up with relationship between member aspect ratio. those days we used to call it aspect ratio, length versus the size or the lateral dimension. Like column you have x dimension, y dimension, and you have length. So, the aspect ratio matters a lot. The aspect ratio is larger is no good, the smaller is better. So, basically based on that they have done quite a number of experiments on circular hollow sections. So, that means you fabricate a pipe, apply the load at which it fails is noted down. Like this you develop several experimental points and come up with a plot, something like this. When you look at this picture, basically you have got several points. This is not the chart for the axial stress, but basically typically you come up with so many experiments and then try to understand the pattern of failures, and then draw a line with a regression analysis. That will be the equation for your future design. So, that is how this formula what you see here is not derived from somewhere, it is basically a regression line defined by the experimental points to take into account the parameters of interest. In this particular case, the parameter of interest is two things. One is the slenderness, which is going to lead to buckling, or the yield stress, which is going to allow the member to yield. So, these two parameters, we just have two equations. The equation 1 is basically the yielding side, whereas the second one is the buckling side. You can distinctly note down these equations. One of them is very easy to understand. The second equation have no relationship with the yield strength of the material. You can see there is no relationship, that means it is a pure buckling. So, that means irrespective of your strength of the material, you can have high strength, you can have mild steel, you can have any, because the member is so slender that buckling is going to govern the design. You see here there is no Fy, whereas the first one you have both the Fy value as well as the slenderness. Now, you carefully note down this. If I make the KL by R ratio very large, big number, so just substitute here, what will happen? If you make KL by R ratio very large, you are going to definitely the detection factor, this is basically here 1 minus something, isn't it? So, that means KL by R ratio larger means you will have larger number to detect, that means it might be the Fy will be multiplied by a smaller fraction, isn't it? Now, the vice versa, you make the KL by ratio very small. When you make it very small, the denominator becomes close to 1, isn't it? And what will become at the bottom, you see here this also is KL by R, this is also KL by R. So, this becomes a smaller number, this also become now. So, you can knock down this. So, ultimately what will happen? You will have only bottom 5 by 3, which will become 3 by 5 multiplied by Fy. So, what is 3 by 5? 0.6. So, basically we end up when the KL by R ratio is very small, means the member is too big, too small, the size is so large, but the length is too small, that means it is stocky member, it may not be governed by buckling at all. So, basically it will reach the value of 0.6 Fy. So, that is the understanding you need to get. So, if I plot this graph basically somewhere here, yes, allowable axial stress in compression for circular cylinders. Basically you see here there are two charts I have made using the same graph what you the equations what you have seen for a different yield strength of material. So, after KL by R ratio of 120, the yield stress has no effect on the allowable stress is no effect on the yield stress, because both are same. Basically buckling is almost governed. So, anything less than 120 you can see a deviation for a lower strength and a higher strength. Ultimately this KL by R ratio is 0, then the yield stress, the allowable stress becomes 0 point. So, the lower the KL by R ratio, you are going to get the higher allowable stress. So, what we are trying to understand here is slenderness play a major role in trying to allow whether you want to allow higher stress or lower stress. As long as you keep this member length quite small, then you can straight away take 60% of yield and then do your computations. Then you make the member longer or keep the length same and make the member too small, then it is not going to be you might think I am doing a very economic design by making the size smaller. That might work, but ultimately it might fail because your cylinderness effects have to be taken into account. So, basically going back to this page of this formula, there are three things you need to remember. Calculate the KL/R ratio, that is basically effective length factor multiplied by length divided by radius of gyration. How do you calculate the radius of gyration? Square root of I by A. So, you can see easily calculate that. I is the moment of inertia in the direction of interest. Remember, allowable axial stress you have to calculate very carefully, taking into account the weakest KL/R ratio. So, for circular section we do not have any worry, because any direction is same property, but if you have unsymmetric sections, probably I sections or channel sections, angle sections or any built up sections which has got the moment of inertia in one axis is not the same as the other axis. So, what we need to see is we need to look at the weaker one, means the larger cylinderness ratio needs to be taken into account. So, that you need to remember, though it is not specifically mentioned here. So, once you calculate the cylinderness ratio, find out a limiting cylinderness ratio beyond which the member will definitely go by buckling. So, you see KL/R ratio greater than a particular value, it goes into buckling, whereas KL/R ratio less than that particular value, it goes into yielding. Now, in here the limiting cylinderness ratio value is very much similar to our Euler buckling, 2 pi squared E by Fy. So, you calculate the limiting value and look at which one is governing, and basically either you go for this or go for this. So, note down here, this is very similar to our Euler buckling load. Euler buckling load for a simply supported beam is pi squared Ei by L square. So, basically that is exactly the same, except that you got a factor of 12 by 23, which is nothing but a factor of safety of 2 approximately, is not it. So, that is exactly we are trying to do here. So, this Euler buckling stress divided by a factor of 2 is given as your allowable stress as long as buckling govern the design. It is not just coming from nowhere, it is basically coming from our mechanics. Only thing is, this first formula is derived as from the experiments using a regression, basically just a curve fitting. If you remember, if you go and do during your MTech thesis, if you do experimental studies on some aspects, you will also do a regression analysis to come up with a polynomial, for example, to fit a curve against the experimental points. Is exactly done the same way. Now, one important thing to note is you need to substitute this Fy value with the calculated value of Fxc or Fxc, whichever minimum, if the local buckling govern the design. So, what you are going to do is look at the d by t ratio, calculate it, and then go to this particular formula to evaluate the local buckling, and basically local buckling is due to axial load. Here we have axial load, and the elastic buckling stress is calculated using this formula, which is basically 2 Ce, the reverse of t by t ratio, and then the inelastic buckling stress is calculated using this formula, and you have to find out whichever is smaller and substitute these values back into Fy. So, we have taken into account the global buckling by KL/R, local buckling by the d by t ratio, and if I plot this graph, I think you will get something like this. Basically, most of the time the elastic buckling stress is going to be very large. So, the inelastic part we have got two charts given for 250 megapascal steel and 345 megapascal steel. So, you will see that most of the time this is not going to be governing. So, you will take the inelastic part and supply to Fy value. Now, you see here the d by t ratio less than 50, you get almost constant value. After that it starts degrading, because if you look at the equation is 1.64 minus 0.23 into d by t to the power 1 by 4. So, basically use such a simple formula. Only thing is you will be using this Fxc value in here. As long as it is less than Fxc, it is fine. If it is going greater, then you will assign the value of Fy itself. That means, if the d by t ratio is smaller, then automatically you will not require to substitute here, automatically Fy will be the value coming there. So, d by t ratio larger means local buckling is going to reduce the yield strength, which you will supply to the axial stress. Hope you understand this idea behind. So, global buckling and the local buckling limits. The next thing what we want to look at is all these charts is extracted from basically the API, based on which some of these equations were derived. So, if you look at this, basically d by t ratio versus the coefficient C, this coefficient 0.3 I have taken, though it is showing a variation like this. Most of our d by t ratio, you see here d by t ratio is 200, 300, we have a d by t ratio is far less than 100. Normally most of the jacket structures we have d by t ratio not acceptable if it is exceeding 60, always we keep the d by t ratio less than 60. So, these are all applicable, the values less than 0.3 or something like this is only for large diameter cylinders, especially for floating structures, like what you have seen in the few classes earlier. We were talking about spar type of platforms, where the cylindrical diameter is 20 meter, 30 meter, 50 meter, and the thickness could be smaller, whereas for structural cylinders we may not be so much useful. Similarly, this is basically the variation of FHXC, which we saw in the equation. No, the equation is 1.64 minus some empirical formula. So, basically a chart. How did they come up with this equation? This equation was arrived, this equation is arrived based on the experiments conducted by so many people, and finally they draw one line. This could be a potential trend. So, I just write down the formula that 1.64 minus 0.23 times d by t. So, horizontal axis is d by t, and vertical axis is the ratio between fxc multiplied by fy. So, basically you read this and multiply by fy will give you the value of fxc instead of using the equation, but the equation is convenient. So, you can calculate accurately instead of reading from here. So, but we need to know how the equation came. The equation is just simply a reproduction of so many experiments that they have done. So, fabricated a cylinder, tested it and then failed, note down the value of load at which it failed, and then repeat the experiments several times. Quite a number of steel, different steel and different projects. These are all research projects sponsored by various government organizations, oil companies, ultimately to produce a usable relationship between d by t and the allowable stress. Similarly, you will see this we have seen the allowable bending stress. Again you see this formula is highly empirical, related only to diameter to wall thickness ratio, and how these equations are arrived basically again by experiments. Unfortunately, we have got experimental results only on the lower range of d by t ratios. The larger range of d by t ratios we really do not have experiments, because nobody got the money and time to fabricate big cylinder and test it. So, you see here that we have got the ratio around 4000. Of course, here fy is multiplied. So, d by t multiplied by fy, please note down it is given in KSI units, so you have to be a little bit careful. So, basically the lower range, quite a number of experiments were done and the curve fitting is done like this. So, using this curve fit, the red line is the ultimate strength at failure, the yellow line or orange color line is the allowable. So, just a division by a factor of safety. So, you see here the equations are arrived basically based on that experimental studies. So, how do we get allowable bending stress is 75% of yield as long as the d by t ratio is less than this. Now, what is this? This is a limit 10,340 divided by fy. So, if you do this you will get a number of somewhere around, if you take a fy value of 50 KSI material in terms of 345 or 350, you will get somewhere around 30. This is from 30 to 60, this is from 60 to 300. So, d by t ratio starting from 30 up to 300, we have got the relationship given here. So, if it is less than 30, you can understand, if you take 1000 mm diameter, what will be the thickness if you want to keep it less than 30? It is 30 millimeter, is not it? So, basically if you want to keep it 100, if it is 1000 divided by 30 will give you how much? If you want to keep it at 30, then you have to have the corresponding thickness. So, if that t by t ratio is less than 30 means maximum allowable stress of 75%, whereas if you keep it between 30 and 60 and 300, considerable reduction is given there, is not it. So, basically it is a quite straightforward calculation of allowable bending stress. So, you take this 0.84 minus this, as long as the d by t ratio increasing, the deduction factor will increase. So, that means the net factor will come lower multiplied by f y. Similarly, here the next range, because if you see this graph, there are 3 linear parts, one is this part, second is this part, third is the last part, and that is why you see here first, second and third. Allowable shear stress straightforward, 40% of yield, no issues. The same thing is plotted, whatever you see here in terms of d by t ratio, I directly plotted instead of. So, you can see here this is 0.75 times f y, first reduction and second reduction, as long as the d by t ratios keep on increasing for 2 different steels, mild steel and the high strength steel. And basically most of the time we do not permit d by t ratio beyond 60. For offshore structures, we keep the d by t ratios less than 60 mandatory, it is by API, because the larger the diameter and wall thickness smaller, you may actually govern by the local buckling, which is no good. So, that is why we keep the d by t ratios less than 60. Now, finally comes, we have done the allowable axial stress, allowable bending stress, allowable shear stress and then allowable hoop stress. Now, what we need to look at is how do we combine these all of them together. The straightforward is the first look at the general case. We have a applied stress and allowable stress. We will be happy and we can conclude if the allowable stress is always greater than applied stress, a linear superposition. So, you look at this particular general case here, if this is applied stress, allowable stress basically taken as maximum, that means there is no buckling happening here, that is the first case where we take tension or there is no buckling happening, plus you look at the second one added is the bending stress divided by allowable bending stress. But what we have got here is a 2 component bending stress, you got a x bending, you got a y bending. Suppose if you have only one bending, then what will happen? One of them will disappear, automatically it will become FB divided by FB. So, what we have done is we have got the axial component acting plus the bending component, but remember axial and bending, the stresses are in the same direction. If you have understood, axial stress is along the member length, bending stress also along the member axis only thing is one portion will be subjected to compressive, the other portion will be subjected to tensile, but the stress direction is along the longitudinal axis of the member. So, there is every opportunity that we should actually combine the stresses. So, you can actually do this way, FA plus FB, you can add them together as long as you can find a combined allowable stress. Can we find a combined allowable stress? Because axial stress is governed by the buckling, local, global and slenderness, whereas the bending stress is governed by the diameter to wall thickness ratio. Nobody have developed an equation for a combined allowable stress so far. That is why we compute the applied stress separately for axial, allowable stress separately for axial, and then applied stress for bending, applied stress, allowable stress for bending separately. Then we find out the ratios and then combine them, because we do not have a facility or a equation or experimental studies done for a combined allowable stress. You understand the idea behind now why we are doing this business. Basically we compute the component. For example, if you have a bending stress is 0, then the ratio here can go as much as to 1. Now, if you have axial stress ratio, so called the FA by 0.6 Fy is the fraction is coming to be say 0.7. So, what can you have it for bending? Only 30% you can. So, 0.7 plus 0.3. So, now you can see here basically a summation of effects of axial plus bending. So, that is basically called the interaction between axial and bending. So, we are just cumulatively adding and linearly superpositioning. Remember, we will talk about this non-linear business later on, because here we are doing only just a linear superposition, axial effect and then bending effect. Now, this is basically a general case, needs to be verified for almost whether it is tension case or compression case. Whereas, if you look at the first two formulas basically on the left side and right side, if it is a predominantly axial case. For example, you take a column, more axial load, but small bending, whereas in this second case here the axial is smaller, very small axial load, predominantly bending. So, we have two situations, either axial load is taking too much of stress or bending load is taking too much of stress. What is really happening when the axial load is less? We have got less problem, because for example, you have a bending load, the beam is trying to bend, or a beam column is trying to bend. Actually, beam means is typically a horizontal member subjected to transverse loading, whereas column means predominantly subjected to axial load. When you have a combined effect, you should call it beam column. So, when a beam column is subjected to a smaller axial load, is better, because buckling may not happen. Remember, when we talk about buckling, global buckling especially, you need to have larger axial load. So, global buckling may happen. So, in that case, you can see here this formula and this formula is same, is not it? Only thing is the allowable axial stress is considered with respect to the slenderness. Instead of taking maximum allowable stress, we take the allowable stress calculated by whatever be the allowable stress as per the axial. Otherwise, this formula and this formula is same, as long as the applied axial stress to the allowable axial stress, the ratio is less than 15%. That means a smaller axial load. Whenever the axial load is larger, you come to the left side, then there is a potential problem going to happen, because of interaction between the axial load and the bending load, which we call it P delta effect. I think some of you might have studied. You remember, you take a cantilever column, apply a horizontal force at the top, what happens? The column tries to bend horizontally, producing a deflection of some amount, it can be so many millimeters. Now, if you have axial load on the same column, what happens is additional bending moment is produced because of that deflection. You understand the idea, no? But in a realistic beam column analysis by elastic theory, you normally do not take into account, you assume that the column is still in the original position when you are trying to calculate the axial stress. The delta effect is not taken. Presence of the bending moment on a column with axial load, the magnitude larger, you produce additional bending moment in addition to the bending moment produced by the horizontal load. For example, if you have the height of the column is h, bending moment for the column is taken as the horizontal load multiplied by h, whereas in this case you will take the delta times the vertical load also produces additional moment. So, basically we call it moment magnification because of so called the larger axial load. Of course, why we are ignoring here, because we say that 15% is too small to cause larger moment. So, that is why in this case we just ignore, whereas in here we take it here. So, you look at the bottom part, especially the allowable bending stress, everything else is same, except here we got a 1 minus something. As long as your applied stress is larger, especially the axial stress, the detection factor for allowable bending stress is coming down. The reason is the magnification of the moment becomes larger and larger because of this bending, and we need to reduce the allowable bending stress. This we call it the moment magnification factor, which is lying at the bottom. Then there is one more factor coming here at the top, is called moment reduction factor, which we will be discussing in the next page. What is moment reduction factor? So, if you look at this diagram, is a single curvature bending, and mostly you have bending moment here, probably different magnitudes, but we all know that if there is a span loading, you have a point load, you may have a UDL load, or you may have other forms of loading, bending moment may be maximum somewhere in the span, we do not know where it is. Now, you see here, this is an unsymmetric bending moment diagram, can be symmetrically drawn like this with the equivalent moment at the ends, but still not losing the maximum moment at the center. We just rearrange the diagram, but still the maximum is at this, but the end moments are not going to govern the design in any case. So, when you are having such a situation, it may not be exactly the same every time. We have got several scenarios. I have just drawn only one scenario, how we calculate the equivalent moment for a particular design aspect. So, this we call it single curvature bending, you may have double curvature bending, and for each case API gives you a recommendation of a reduction factor. Instead of taking the full maximum, you find out the equivalent maximum multiplying by the end values, and a reduction factor of Cm equal to 0.85 or the ratio between the end moments or the other factor. So, the three cases given. Most of the time for primary structures we apply a reduction factor of 0.85. This is given by the codes. So, if you look at this formula, everything else is same except you have a moment magnification factor and you have a moment reduction factor due to equivalent moment. For asymmetric sections, you see here the difference is very simple. You split into this formula is split into two components, that is all. Basically Fx bending moment, Fy bending moment, otherwise it is the same. So, all the formulas are arriving from basically a simple formula of Fa by Fa plus Fb by Fb, combined effect must be less than 1. So, all of them are basic principle is very simple, linear superposition of the stress ratios should be less than 1. So, this is basically called axial compression and bending. If it is tension, then there is no worry about anything, straight away you can use this formula, because this interaction all will not be there. This the term appearing here, so called Fe prime, is nothing but our Euler buckling stress. The formula is given here. Now, the effective length factors given by API, I have just taken the API table. This table what you see in the right hand side is a table extracted from API for different scenarios of I do not know whether you are able to read, you can see in the notes. Basically for structure columns, superstructure columns, effective factor is 1, jacket legs also 1, that means 1 means the distance from the point, this point to this point, you should take it as full length. And for various other scenarios like braces, say 80% and 90%, basically the effective length for 100% fixed members you can take it 50%, isn't it, because the effective length factor is half. Whereas in this particular case you see here we have not gone to 50%. For example, you take a brace, this brace, any one of the brace, we are not going for 100% fixity, because this connection is not producing the sure fixity there, because you got a hollow section at the end. So, you may actually have a deformation and rotation. So, that is why it is less than 1, but not necessary that it is 0.5. Only theoretically you will have effective length factor of 0.5, whereas most of the practical designs we may have 0.6, 0.7, 0.8, depending on how much rotational restraint you are able to achieve, whereas in tubular construction achieving 100% rotational restraint is very difficult. Some of the graphs extracted for basically the FHC and FHE. So, we just saw earlier, all those are API graphs, the equations what we discussed. Now, what we are going to look at is the hoop stress, allowable hoop stress. Basically what we need to do is we apply the hydrostatic pressure externally. This formula is very similar what we have seen earlier, the hoop stress due to applied axial stress. Similar, only thing is the coefficient C, instead of 0.3 what we have taken earlier, it will be calculated based on d by t ratio. Basically how we calculate is a parameter called m, is the length to diameter, is very simple. The larger the diameter, lesser the m, larger the coefficient. So, you see here if the m value is less than 1.5, you have a CH coefficient of 0.8 compared to what we have used 0.3 for axial buckling. So, here if you keep the m value is less, for sure you are going to get the higher elastic buckling stress. Basically you see here L by d, of course you got d by t inside with a square root. Now, you see this, there are 4 segments or 5 segments given here. If you plot this one in a graphical manner, supplying d by t ratio as one of the parameter with the parameter m here, you could see here the buckling coefficient is 0.8 maximum when the parameter m is, we call it geometric parameter, this m is geometric parameter, basically length versus diameter. So, the buckling coefficient reduces to almost 10% when the m value is around 8. So, you can see here length to diameter, if you keep it smaller, then you have the larger buckling coefficient. After that it becomes almost less than 5%. that means local buckling is going to govern the design. We should never ever do that. The idea behind is, first you calculate the L by D ratio, length is the length of the member. Suppose if you fail to do that, for example, you go to this diagram. So, the original length of the member is like this, but then what actually can prevent this member from local buckling? You provide rings like this. You see here in tiny dots, basically we have a circular rings preventing the pipe from becoming this way, that waveform. Oh, where it is, something like this. So, as long as you will provide a ring in this location, for example, in this location you provide a circular ring, the pipe will not be able to buckle, because the rings will hold it by taking as a shear force. So, the idea behind is, if you provide rings, you could get additional stress. So, in this equation, either you take the initial length or the length of rings spacing, basically one ring to another ring. So, the M parameter can be controlled by means of introducing additional rings, not necessary only to introduce a structure to be attached to, because it is only a local, it is not a global buckling. So, then the critical hoop buckling stress is relation to the elastic buckling stress. Basically, as long as is less than 55%, you take the elastic stress as the buckling stress, and there are two more ratios given in the range of basically 55% to 160% FHE. You use this empirical formula. These are empirical formulas for which the charts are given here. I think these charts basically developed, those equations are derived from this chart, and large range of experimental points. You can see here how many experiments have been done for this kind of. You fabricate a cylinder, apply external force until failure, note down the failure load, and basically develop this chart based on that type of principle. So, basically the three lines what you see here, these lines were coming from that particular experimental points. So, once you achieve this, then we can do the interaction. I think we will discuss this one tomorrow.